So are there any questions regarding what we did in the last class? We have covered the different stochastic models and how to simulate them. In particular, we talked about the variance gamma models, which were reasonably involved, but are the schemes clear?
The schemes are clear, sir.
Okay, so if as and when required, you can write a code and do the simulation, right?
Yes, sir, probably.
Okay, because there will be assignments like that. So, okay, so now let me tight up things a little bit. So how do we do the simulation analysis in general? So we have talked about different stochastic models. We have talked about different strategies for approximation and bringing them together. So I have some approximation techniques and I have some stochastic models which are common. So I use them in some combination to come to a analysis plan. So how does it go in general? So basically, once we have decided on the discretization scheme, we need a general algorithm for derivative pricing. And we saw in section 1.3 that most of these pricing problems are essentially like calculating expectations. The expectations of this form, expectation of fx capital T, where f is the contract I'm interested in, x small t is the usual value of the underlying security, and capital T is my maturity time, or either maturity time or some important time point. And the expectation E has to be taken under the right measure. So we have to adjust for risk neutrality, etc., and calculate the correct expectation. And that expectation we call theta. So generically, our objective is to get a good estimate for theta. So this is a general algorithm to estimate this expected value, estimate this theta. So I have n steps, so n many simulation, n many time points where simulation needs to be done. I start with x naught, set t equal to 0. Now, for I equal to 1 to m, so for each time step, now I simulate a normal random variable, let's say, because whatever we are going to do, we are going to simulate for some random distribution. And I calculate x hat as the SDE step of x hat and small t. What is this SDE step? This SDE step is the discretization function based on whatever scheme that we have chosen. Then we go to the next time point and so on. Finally, after we have created the n many paths, fj is f of x hat. So each path yields one value of f. So my estimate of the expectation, estimate is given by theta hat n, will be a simple arithmetic mean of all the edges. And also I can estimate the corresponding standard error with the usual formula. So this is the generic algorithm for handling any derivative with some discretization scheme. So the discretization scheme details are hidden in this SDE step, which we have talked about earlier in different forms. My timeline is broken down into capital M steps, and I am simulating capital N many instances. So I am simulating N many paths, and I average over the paths. That's how in general it works. And once I have this estimate for the standard error or the variance, sampling variance, I can also use the usual CLT to get a confidence interval. So if I want an alpha % confidence interval, I can use the standard normal distribution bounds to create a confidence interval for my theta. So that is the standard thing, and this is absolutely simple. This also implies that my confidence interval, which I want to make as tight as possible to make the estimate more accurate, my confidence interval can be made tighter if I can reduce the variance, this sigma square n hat, using some strategy, or I can increase the number of simulation paths, because my length of the interval is proportional to 1 by root n. Now, increasing number of simulation paths is more expensive. So our primary target would be to find strategies so that we can reduce the variance. So now we will focus on certain variance reduction techniques. So we have a fixed budget, so we can only create so many paths. So let's say we cannot increase capital N too much, but using the same computational resource, can we devise a strategy which will give us a lower variance, which would also make the interval tight. So what are the variance reduction techniques that we will be talking about? So as I said, so simulation methods are flexible, but the cost is typically the highest among all the other strategies. I can improve the accuracy in two ways. I can get additional samples, which is expensive, or reduce the variance. Typically, the variance reduction methods works in the following way, that we use information about the pricing problem or the model to adjust our simulation strategy. So we do not do simulation without any restriction. We try to put reasonable restrictions on the simulation, or do the simulation in a certain way. We get the same capital N many samples, but how do we get them is the trick. So what do? We allow our estimator to take advantage of whatever information we have. So we apply the use the randomness in the most efficient way possible. So let us see. Let us just try to talk about some of these methods. Some of these methods might be known to you. The 6 common methods that I am going to talk about are control variate, antithetic variates, conditional Monte Carlo, importance sampling, stratified sampling, and use of common random numbers. So now before I begin, how many of these are already known to you? I know you are familiar with importance sampling and acceptance rejection strategies, those kind of strategies. So are any other methods already known?
No, sir.
Oh, they are not known. Oh, okay. Okay, so then we will talk about them. Of course, we are going to discuss them in a very informal way, because I don't want to get into too much of the statistical methodological details. Our focus here would be on to get the basic concept and how to apply it in our present context of financial contract pricing. So let us start with the control variate method, the first candidate here. So control variate method works in the following way. Our target is, of course, to estimate theta, which is expectation of hx, where h is the target function. Now assume that z is also an output of the simulation. So when I do the simulation, I get some byproducts. Z is the byproduct. And moreover, assume that expectation of z is known, 1, and 2, z is correlated with the random variable whose expectation we wish to find. So I have a target random variable, and z is somehow correlated with it. Then we can construct a new unbiased estimator of theta in the following way. Suppose theta hat is equal to the usual estimator y. Y is typically the simple arithmetic mean. So if I generate n many paths, I will just take the simple average. That's my usual estimator. Define a new estimated theta hat c, which is y plus some c times z minus ez. This c I have to choose. Now, because I have only added a mean-centered random variable here, expectation of theta hat c will also be theta. So theta hat c is an unbiased estimate. Now, can I make the variance of theta hat c less than that of theta hat? And if you look at this, you can immediately identify that you can do it very easily. Suppose C star is my optimal value of C such that variance of theta hat C is minimized. Then just using the usual regression type argument, I can show that then at that C star, variance of theta hat C star would be variance of theta hat minus this quantity. So this is just the regression problem that we have learned to solve from our very first year. Do you see how this is working? I have already said that Z is correlated with Y. Z is correlated with the random variable that is our target, so it is correlated with Y. So I use that correlation to regress out, sort of regress out the effect of Z, which will reduce the variance. Is this argument clear?
Sir, is this Z in some way related to the instrumental variable concept?
This Z, okay, so let me put it another way. So instrumental variable concept is another application of this same concept. This using correlation is a very general idea. Instrumental variable application is one such idea. Control variate is another such idea, but they both rely on the same principle. That if I have correlated random variables, I can use the regression and look at the residual sum of square. That is what we are using here. Instead of the whole variance of theta hat, I am regressing Z out so that I get a residual sum of square, which will be less than the original variance. So variance of the new estimator will be less. Okay, is that
Okay.
Does it make sense?
Yes, sir. Yes.
So control variate then relies very crucially on being able to identify a Z, which is a byproduct of the random number generation process and which is also correlated with the target random variable. So it will definitely depend on the situation. So in the exercises, there are examples where you have to identify a control variate and then come up with a strategy to reduce the variance. But one thing is clear, that if this correlation is anything not equal to 0, any non-zero number, then the variance will indeed be lower than the original estimator. And stronger the correlation, better the estimate. So that's the control variate strategy. I will call them strategy because it's a very simple method. It just uses regression, but the idea is important in the sense of our objective, variance reduction. The second method is also related to correlation, which is called antithetic variates method. So what is antithetic variates? When we are drawing random samples, we are essentially creating different copies of our estimator. We can create different copies of our estimator. Now, suppose I have created two copies, y1, y2. Can I use the correlation between this y1, y2 in some way to reduce the variance of theta hat? I will be able to do that if I can make sure that the covariance between y1 and y2 is negative. See, if you have simple random sample, then you know that the variances just get added up. covariances are 0. But if I can somehow induce a negative correlation, then those covariances will be non-zero. They will be actually negative. So the variance of the sum will be less than sum of the individual variances. So that way we will be able to save on variance. That's the standard logic. So how do we do this is the question. So typically, if we can induce negative covariance in the samples, then this can be done. How? One very easy method to do this in most of the simulation situations is that, you see, any simulation is after all using the uniform sample. See, when we discuss the random number generation from different probability distributions, we started from the uniform 0, 1 random variable, then use the inverse transform method to generate random variables from whichever distribution we want. Now, suppose I draw U from uniform 0, 1. Then I know that U and 1 minus U have the same distribution and they are perfectly negatively correlated. So it's a pair which is perfectly negatively correlated. They come from the same distribution. And now I use them as the basis for my inverse transform method. Inverse transform method is typically monotonic. So the negative correlation between U and 1 minus U will be preserved even after transformation. After F inverse U and F inverse of 1 minus U is computed. So I get a pair of random numbers from the target distribution which are negatively correlated. I can also do it very easily if I have a symmetric distribution like the normal distribution. I generate an x from normal 0, 1. If I simply take minus x also, minus x comes from the same distribution. And I have induced perfect anti-correlation. So this is a very easy way of generating random samples with induced negative correlation. Now I will apply my pricing function h on these samples. When I apply my pricing function h, it may reduce the effect of the anti-correlation, negative correlation somewhat, but it will not eliminate it altogether. Even after the transformation, it will preserve some of the negative correlation, and hence, in the final analysis, it will reduce the variance. Okay. So is this method clear? Again, this method is using the idea of inducing negative correlation, but now it is inducing the negative correlation directly in the random number that is generated. I can do that either starting from the uniform distribution, or I can do it directly on any symmetric distribution. Okay, is it clear?
Yes, sir.
All right. So then let me move on to the next strategy, which is conditional Monte Carlo. So what is conditional Monte Carlo? Again, it uses a related variable. So conditional Monte Carlo is based on conditioning the expectation, which is our primary target, our contract value, on as much information as possible, which is either known explicitly or which can be calculated easily. So again, we are thinking of a related variable z. We are looking at a related variable z for which I have the information explicitly already with me for some reason, or z is such that its properties or the information from it can be calculated very easily, more easily than that on y. If it is such a situation, then I can use this z to reduce the variance of the resulting expectation, because I know that if I use conditional expectation, I will be able to reduce variance. So this is the idea of the conditional Monte Carlo. So I need a Z which can be very easily simulated, which I can study very easily. I look at a function gz, which I call v, which is nothing but the conditional expectation of y, which is my target, the actual target, given z. So I need z, which can be easily simulated, and I also need this function gz, a conditional expectation that can be computed exactly. So if I can do that, then I can use this algorithm, this conditional Monte Carlo simulation algorithm, that I want to generate n many paths. I generate zj. Zj is like this new variable. Using zj, I compute the conditional expectation of y given zj, which is g of zj, which I call vj. Finally, I calculate this estimator, theta and cm. Cm is the conditional Monte Carlo, which is simple average of all the v values. And the variance, sampling variance, can also be estimated like this. Typically, we know that conditional expectation reduces variance. So if we can select our z properly, we will be able to show that sigma square n comma cm, this new sampling error, sampling variance, will be less than the unconditional sampling variance. So that's the general idea. Again, the idea relies on regression-like methodology. So in that sense, my conditional Monte Carlo and my control variate methods are based on the same principle. So that is conditional Monte Carlo. And again, it will require identification of a particular variable z with these properties, that I can simulate it cheaply and I can compute this conditional expectation exactly. Okay. Next, I will talk about importance sampling. So importance sampling, formally or informally, you have heard of before, I'm sure. Maybe informally, because the name may not be familiar, but the idea is actually quite simple. And by the way, importance sampling is actually the most powerful method of variance reduction that is available to us in statistics. So this method is based on using knowledge of the pricing problem to focus our sampling on critical areas of interest. So I have this whole support for my random variable, for my target random variable. But from the nature of the contract, I know that some subset of this support is actually more important to me. So if I am looking at a call option, basically the region above the strike price is more important to me, because that is where the call option will be exercised. And similar situations will arise for other contracts. So what do? We want to focus our sampling on critical areas, values of the underlying variable which yield important results, and which in turn reduces the variance of our estimator. So if I can get more samples there, I can reduce the variance. One easy example, one obvious example of this is out of the money options, where payoffs only occur at very large or small values of the underlier. And so sampling in these regions makes our estimator less variable. So I'm looking at, say, a call option where the current stock price is very much below the strike price, which means conditioning on the current stock price, exercise probability of the contract is low, because values above the strike price X now has very low probability. But that is the region which is very important to me. So I want to oversample from a low probability region. That's the basic problem. Okay. So little bit of notation. So suppose we are interested in computing this theta, which is expectation of hx. H is our target function under the probability function f, density f. X has the PDF f. let G be another PDF with the property that Gx is not equal to 0 whenever Fx is not equal to 0. So they have the same support. If that is true, then I can write theta in the following way. Write theta as this usual expectation integral, but now insert Gx in the numerator and denominator so that I can rewrite this expectation as expectation of a new function H star, where H star is nothing but H into F by G under the new probability function G, where this F by G is known as the likelihood ratio, and this should be easily computable. So we need to choose our G in such a way that the ratio is easily computable. Why do we need to do this? This has very important implications for estimating theta. So in our original estimation algorithm, we generate capital N samples of X from F, the original function F, and we set theta hat N equal to the simple average like this, HXG. In the alternative algorithm, where I am using G, we generate capital N values from G, because G is the probability under which I am calculating my expectation. And we set theta hat N IS. IS is for importance sampling. Theta hat N IS as arithmetic mean of the modified function H into F by G. Then theta hat N IS is our importance sampling estimate. So this is our new function. So now we want to show how to reduce the variance. So I have this new theta hat N IS. Now my job is to select my G in such a way that the variance of theta hat N IS is less than the original theta hat N. So variance reduction via importance sampling. Now variance reduction is achieved by first observing that both of these expectations must be the same. They both give me theta. But they use two different functions, H, where I use the F function, F probability, H star, where I use the G probability. The variance of our new estimator, importance sampling estimator under G, is given by this expression, H star square G dx minus theta square, which I can write as this ratio times fx dx minus theta square. So basically it is like calculating the variance of this altered function H square F by G under the F probability. Now variance of H under F, which is our alternative estimator, that is straightforward, H square Fx dx minus theta square. So we are looking at the quantity, which is our supposed reduction in variance, given by variance under F of H minus variance of H star under G. So this is the supposedly reduced variance. This is the original variance. So their difference is my reduction, my payoff, my benefit from using importance sampling. And the expression for that can be analytically written explicitly as H square 1 minus F by G Fx dx. Okay. This expression is clear?
Yes, sir.
Yeah. So what I want to do is I want to make this quantity positive. I want to make this quantity positive, in fact, as large as possible, because that would give me the variance reduction I'm looking for. And now, because of this explicit algebraic form, I can prescribe that we should choose G in such a way that whenever H square into F is small, I can choose F by G greater than 1. And whenever H square F is large, I can make F by G less than 1. You see, both F and G are density functions, so they have the same support. They both integrate to 1. So in some range, f will be bigger than g, but in some other range, g must be bigger than f. It has to be because the integral of both are the same over the same support. So then I need to cleverly choose the region where I want f by g to be small. So obviously, wherever I have more weightage, wherever h square f is large, they have more weightage in my integral. So in those regions, I will choose f by g to be small. So I will choose g to be larger than f in those regions. In other regions, I will compensate by choosing g to be smaller than f. G is in my control. So I will choose g to be larger than f, where I have more mass. Mass in this sense, not in the original density, but in h square into f sense, where both of these things are known to me, and give less mass to the remaining region. So let us say that there is a region script A where h square f is large. Then by the above argument, we would like to choose g so that f by g is small for all x in script A, which means we would like a density g that puts more weight on the set script A. So script A set will get more weightage from density g compared to density f. So that is the strategy by which I will be able to make this integral positive and hopefully much bigger than 0. But it will depend on a clever choice of g. That is for sure. Okay. So is this strategy clear? What we are trying to do and whether we are able to do it?
Yes, sir, it is clear.
So it is just a simple arithmetic strategy, but knowing the functional forms, this arithmetic strategy can be implemented. So the implementation is important because again, if the implementation is unclear or if it is very complicated, that also eats into computational time. But here it is simply based on this product, so computational time will not be too much. One very important application of this, which we'll discuss in an example now, is that when h involves a rare event. So suppose my function is such, h function is my contract, h function is such that it is equal to 0 over most of the state space. So it is actually involves a rare event. So most of the time it is 0. It can then be particularly valuable to choose a g so that we sample from that non-zero part of the state space more often. So we put disproportionately high sampling weightage on the small space where hx is not equal to 0. Because it's a rare event, so hx not equal to 0 has actually a very small mass. So we want to get disproportionately larger samples from it. And note that if we choose g to be hf by theta, suppose by some magic I knew about theta, so I choose g equal to hf by theta, then I get a perfect estimate. Perfect in the sense the variance will be 0. But of course, that never happens. Theta is never known in reality, and that is our target. So what we really try to do is that it gives an idea about the shape of hf. So if I can put g close to this shape of hf, because hf by theta was our target, and theta being a constant, the shape of g should be same as shape of hf, shape in the sense of curvature, etc. So if I can match g to the shape of h into f, the variance is likely to be lower. So that's a strategy for targeting a good candidate for g. So that is how importance sampling works. So importance sampling works on 2 features. One feature is that I want to distort my sampling weightages. I want to distort the sampling weightages in a particular way. so that this integral becomes large positive. And the second thing is that in order to achieve this, I need to look at the nature of the function h into f. So if I can match my g with h into f, I hope to get a better candidate, which means I hope to get lesser variance. Now let us look at a quick example. It's a very simple example, but it illustrates the use of importance sampling very easily. So this example talks about estimating a rare normal event using importance sampling. What is this rare event? The rare event is probability that x is greater than 8, where x follows standard normal 0, 1. And you know that this is a very, very rare event. If you want to compute the probability of such an event, there will be many zeros after the decimal point. So if I want to simulate, I want to use the usual simulation to estimate theta, usual simple simulation, we will most often get 0 as my estimate. Because this event is so rare, even if we draw 10 lakh samples, there may not be any event like this. So my estimate will remain 0. But we can improve this situation very easily if we use importance sampling for estimating this particular theta. So what do? We will use importance sampling with a new random variable y, which follows normal mu1, where we will choose mu. So we basically shift the center of the distribution by an appropriate choice. So what will we get? This is our original target object, probability x greater than 8, which is indicator that x is greater than 8 under the expectation of the indicator is greater than 8 under probability x. And this is a very, very rare event. So this expectation is very, very small. So estimates will most often be 0. Now this is equal to this integral. I just write the normal 0, 1 density here. Now what do? I insert g in the denominator and numerator. My new g has mean mu. So this is my f by g ratio, and this is my g. Now f by g ratio will give me this expression after cancellation, e to the power minus mu z plus half mu square. So instead, I am calculating the expectation of this new indicator under g. This new indicator is that x is greater than 8 into e to the power this. So I have two parts in my expectation. I have the original indicator, which happens rarely, but I also have a new quantity e to the power minus mu x plus half mu square. And this I can make slightly bigger. How do I make it bigger? So G is the probability distribution normal mu1. And if you just look at this problem, it is very easy to say that an optimal choice for mu would be mu equal to 8. So I shift the center to that rare point 8. So if I put mu equal to 8 here, I will be able to get the maximum for G, maximum impact from G, and I will be able to estimate my theta in a much better way. So what I do is, instead of sampling from normal 0, 1, I sample from normal 8, 1. And then x greater than 8 will happen 50% of the time. And then what I do is, I discount the indicator with this e to the power function, which is easily computable. So I can calculate the expectation under G quite easily. So just by a simple change of center, simple change of base, I can move to a situation where this event is not rare at all. I can get enough samples and I make the necessary adjustment. And as I already mentioned, if you understand this example, then you can also see that this would be very useful in case of these deep out of the money options also. Because deep out of the money options are exactly this kind of situations where I am so far below the strike price that achieving anything above the strike price has become very rare. So if I use a direct simulation technique, I will not get samples. So this kind of an important sampling strategy would be very useful for deep out of the money options. Okay. Is it clear?
Yes, sir.
All right. So let me also talk about stratified sampling methods, which we all know, thankfully. We all know what is stratified sampling methods. So stratified sampling essentially requires us to, so basically the situation is where the population is not homogeneous. There are different regions of population with different properties. I stratify the population in such a way that within a stratum, the population is more homogeneous. So I can now select my weightage for each of the stratum so that I am sure of getting a better representation for all the varieties in the population. That is how the stratified sampling method usually works, and that's how we learned it in the sampling techniques courses in our undergraduate days. So typically it would indicate that I sample more from regions with high probability and or high volatility. That's the usual situation where stratified sampling methods are used. The drawback with that is I cannot ever be able to observe the optimal NI stars. So NI stars are my sample sizes for IX stratum, optimal sample sizes. But I can never observe optimal NI star because then I would need to know sigma I in advance. And obviously sigma i's are not known. So all I can do is I can try to estimate sigma I from some pilot sample or maybe from other related information. And then using estimated sigma I, we can get a good approximation for NI star. That is how the stratified sampling method works. If we know that the population density varies greatly within a division, stratified sampling will ensure that estimates can be made with equal accuracy in different parts of the division, because I can use NI stars or some sample size close to NI star so that I can equalize the variance in all the spectrum. And then the comparison of subregions can be made with same statistical power. So I can equalize the power in all the regions also. And that is where stratified sampling methods are important in pricing derivative contracts. Because when we are looking at a particular derivative contract, we know that certain regions are less important, certain regions are more important, and certain regions are less volatile, where the value of the contract doesn't vary much, and some regions where the value of the contract varies a lot. So obviously, if I want to equalize the power of estimation in all the strata, I would like to allocate more samples in the more variable or more volatile region and allocate less samples in the less volatile region. So that's how stratified sampling is useful here also in our financial calculations to reduce variance. Finally, I did not have a section for the common random numbers because common random numbers, there is no detailed methodology. Yes. Yes, any question? Okay. So I said that there are 6 methods and the last one was common random numbers. So common random numbers is simply the following strategy, that suppose I have a simulation algorithm which has many different runs, and in each run, I need not really generate a fresh set of random numbers. The same set of random numbers can be reused. So if I see that there is no linkage between the different runs, so I can use the same set of generated random numbers in different runs. If the algorithm is of such a nature then a very common and very time-saving strategy is to generate one set of random numbers in the beginning, outside the loop, store them, and then in each of the run inside the loop, use the same set of random numbers. So that method is called the common random number method. And this is really, really important when you are generating a large number of chains, maybe 10 lakhs of chains, and within each chain, you need 1 crore or 10 crores of random numbers. So if you are going to generate all of these afresh, then you will need maybe 10 to the power 12 or 10 to the power 13 random numbers. But if the different chains are not related to each other, you are able to use the same set of random numbers, then you are able to reduce the random number generation algorithm to 10 to the power 7 or 10 to the power 8, which is a huge saving in terms of computational time, CPU. So these are the methods which we commonly employ in reducing variance when our computing resource is limited. We have fixed our capital N. We do not want to increase capital N anymore, the number of chains. But given that resource, we want to make the optimal use of it in reducing the variance or sigma square F. Okay, any questions here? So are these methods clear?
Yes, sir. Just need to go through them all.
Yeah, of course you need to go through them, certainly. So, but I'm almost at the end. So what do we do? Do we take a break or should I just continue today? And if you have questions, you can ask me later. Which one would you prefer? Maybe I can just continue because I just want to talk about this table and then I will be done. So we will finish the class early, and if you have questions, you can always ask me later. Okay, so this is the table that I wanted to show you finally before we sign off. So what is this table about? This table is about the use of different pricing schemes under different models using different methods. So this is a comprehensive table which I have taken from chapter 7. So this is the first table in chapter 7, which gives a complete summary of what are the different techniques that are usable for different contracts under different models. So the way to read it is in the following way, that suppose I am looking at equity, foreign exchange, commodity, or credit derivatives. So derivatives where the underlying are equity, which is stocks, foreign exchange, currency, commodity, all the commodities we discussed, or credit. So interest rate derivatives. So for all of these situations, suppose my model is given by the geometric Brownian motion, simplest model, or more complicated models like Heston or variance gamma or CGMY. I can deploy any of these models in these situations. What are the pricing methods that I am able to use? The methods that I have learned. We have learned transform techniques, and we know that transform techniques are not applicable in all contexts. So where can we use transform techniques? So if I have vanilla option, vanilla contracts, path independent, then wherever I see a tick, the transform technique can be used to price a contract, a vanilla contract, under these models, GBM, Heston, variance gamma, CGMY, etc. If I have weakly path-dependent contracts, we have discussed some of them, which can be approximated under the transform techniques. I am still able to price derivatives under these models where I have a tick. But of course, if I have a properly path-dependent exotic option, transform techniques cannot work. We know that. So these are all crosses. Moving on to the next method, which is the method based on PDE or PIDs. So we are using numerical approximation techniques here. I have a better situation. I can not only compute the vanillas or the weakly path-dependent options, I can also price most of the exotic options using PDEs or PIDs. And finally, with Monte Carlo simulation, I can do most of the things except where CGMOI models are involved, because CGMOI models, Monte Carlo simulations are not very stable. There are convergence problems. So under CGMOI model, you are better off looking at the PDEs or PIDs rather than doing Monte Carlo simulation. Similar classification is done also for the one-factor models, which I learned in the CAPM model last semester, or its generalization, the arbitrage pricing models, as in the n-factor models. And there also the common models are covered, like NIG, Vasicek, Hull and White, etc. And this table gives us a summary of what kind of contracts can be priced using what kind of technique. So for vanilla, weak, and exotic option contracts, whether I can use transforms or I need to use PDEs, PIDs, or as you can see, in all of the cases, Monte Carlo simulation will work as we claimed. It is the most expensive, but most general. But in some of the cases, PDE, PID methods will also work. And in a few restrictive cases, transform techniques are also fine. So, okay, so basically that brings us to the end of our syllabus. So I said that we will do up to chapter 6. Chapter 8 I am not including. So this is the end of the syllabus. We will finish the class today unless you have something to ask. So regarding the variance reduction techniques, you can just look it up. They are also useful in high dimensional computational strategies in other contexts also, not only in finance. So maybe some of the strategies you will be learning in computational statistics courses, and you will learn about different applications of them. So if there are questions, clarifications, I will be available for discussing later on.